Hello everybody. Today I am going to discuss some advanced topics like tangent and normal. Let me first define the tangent. Generally, most of you have the idea that if a function is has certain derivative like dy dx at certain point, then from that derivative quantity we get the gradient of the tangent, and ultimately we are able to find the equation of the tangent by certain formula. But that is actually the process of obtaining the formula of the tangent, not the definition of the tangent. Okay, so let me define the tangent first for a given equation. For any given conic, let me show you a picture. Consider this kind of picture. Suppose this curve. This is the curve. I am denoting. I am writing it by certain say green line. Hmm. And in this curve, we have a point P. This is the point P. Hopefully, this cursor is visible to you. This is the point P, and we draw any arbitrary straight line through this point T. Through this point P, we draw any arbitrary straight line, and that straight line would at most cut the curve represented by a second degree equation in 2 points. So one is the point P, of course, and another is the point Q. The question is that is there any third point of intersection? The answer is, if the curve is given by a second degree equation like this kind of equation, we shall prove that we may have at most 2 points of intersection. One may be the point Q, another may be the point, one may be the point P, another may be the point Q. No third point of intersection is there when the equation of the curve is given by a general equation of second degree. We are discussing all the curves that would be represented by general equation of second degree. If it is third or fourth degree curve, then we may have third or fourth point of intersection, but currently we have only 2 points of intersection. One is the point P, another is the point Q. Now, suppose this point Q is now moving along this curve towards the point P, okay, not along the straight line PQ. If the point Q moves along the curve represented by this green curve, then the limiting position, you see, just this would be the limiting position of the straight line PQ. Then this limiting position would be the tangent to the curve. Got it? The limiting position as the point Q moves along the curve P, along this curve towards the point P. As the point Q moves along this curve towards the point P, okay, then the limiting position of this straight line, this direction, this would be the limiting position of this straight line PQ, okay, this straight line PQ. This red line would be the limiting position of this black straight line PQ as the point Q moves towards the point P along this curve. Then this limiting position, that is actually the represented by this red straight line, this limiting position would be the tangent to this curve, provided that limiting position exists at all. The limiting position or the tangent does not always exist. Remember this result. Okay, so if such curve or if such straight line, limiting straight line exists for a certain curve at certain point P, then only this kind of straight line is called a tangent to this curve represented by this green line at the point P. Is it clear to you?
Yes, sir.
Do you have any other question regarding this definition?
No, sir.
Okay, so in future, if anybody asks about the definition of tangent, don't ever say the definition in terms of dy dx. Got it? If the function is not differentiable at the point P, even then sometimes we are able to draw the tangent. There are certain special kind of curves that we will discuss in our higher study. But over here, don't ever say that if dy dx exists and all, then we get the tangent. That is the result for a particular case when the curve is differentiable. But sometimes the curve is not differentiable. Even then, the idea of tangent can be defined. This is the equation of a straight line. When a straight line passes through certain fixed point capital A having the coordinates a comma b, and suppose P having coordinates x comma y is any arbitrary point on this straight line. Suppose this is the x-axis and this is the y-axis, and theta is the slope of this straight line with the positive x-axis. Okay, and if and the distance in between A and the point P, if this distance is equal to the distance r, small r, in that case we know that this much distance, that the base of this triangle, that would be is equal to r cos theta, and the perpendicular of this triangle would be is equal to r sin theta. Okay, and as a result, we will be able to write x is equal to a plus r cos theta and y is equal to b plus r sin theta. I am not going to deduce this result. I am just discussing all these results. You already got these results in class 11 and 12 level geometry. Or in other words, we can write this x minus a by cos theta is equal to y minus b by sin theta is equal to r. This first expression is called the parametric equation of the straight line. What I am trying to say is that any point on the straight line can have these two kind of representation. Got it? And this much distance r would be very important in this kind of representation, that cos theta and sin theta, these are actually called the direction cosines. The idea of direction cosines will be introduced in your three-dimensional geometry, but whenever that idea is converted in two dimensions, we get cos of theta and sine of theta. Got it? For the time being, you just need to remember this idea of direction cosine. That's all. Hmm. Cos of theta and sine of theta, actually these are called the direction cosines of this kind of straight line. So the idea is that x is equal to this coordinate a plus r into cos of theta, one direction cosine, and another is y is equal to b plus r sine theta. Sine theta is also called another direction cosine. Hmm. Or you can say that x minus a and y minus b, these are divided by two different kind of direction cosines, and that would give us the length, this length in between a and p. Now you all know this equation, but we now need the application of this idea in our further study. Okay, what is this? You see, suppose the point, we have a fixed point capital A. This is suppose the fixed point capital A, and through this fixed point we are drawing a straight line, and that straight line we are going to prove that Mathematically, this straight line will cut a curve given by this kind of equation number 1 at most at 2 points. One is the point P, another is the point, suppose, Q. So let's prove how is it possible. I am drawing this figure geometrically, but mathematically, without the help of geometry, I am going to prove this result. How to prove this one? Suppose this point capital A has the coordinates x1, y1. Got it? Then the straight line would pass through this point x1, y1, and so this equation x minus, in place of A we have x1 and in place of B we have y1. So x minus x1 by cos theta, that is equal to y minus y1 by sin theta, and that should be is equal to r. Okay. Now for our convenience, we are writing cos theta is equal to L and sin theta is equal to M. So that this equation can be written in this form: x minus x1 by L is equal to y minus y1 by M, that is equal to r. Now, if we consider or if we compare this first ratio is equal to r, in that case, we will have x is equal to x1 plus L into r. Similarly, if we compare second ratio with this equal to r, then we will have y is equal to y1 plus m into r. Now, if we put these two expressions of x and y in equation number 1. Got it? In equation number 1, if we put these two expressions, we will have this kind of expression. Okay. You see, in place of x, we are putting x1 plus L into r. Similarly, in place of y, we are putting y1 plus m into r. Got it? Now we expand this equation and rearrange them. What we shall observe that there are certain r square related term, then we shall have certain simply r related term, and remaining would be free of this small r. Remaining term would not containing any small r at all. Got it? So we can say that this is a second degree equation in R, and therefore we expect that if we solve this equation, we expect at most two real roots of R. It may so happen that the roots are complex conjugates, then we don't have any problem. But if these are real, then both of these two roots must be real roots. Now suppose these real roots are equal to R1 and R2. The real roots of this curve, of this equation, become R1 and R2. Then what would be the geometric meaning? For R is equal to R1, we will get 1 point, and that would be this point P. Got it? And for R is equal to R2, we will get another point, and that would be this point Q. So for different roots of this equation number 3, for different roots of this equation number 3, we will have two different points P and Q. So as because this is a second degree equation, we would never get three roots of this equation. Therefore, we can say that we would never get three different point of intersection. This is one point of intersection, this is another point of intersection. Okay, so we would not get three different point of intersection. We will maximum, at most, we will get two different points of intersection. It may so happen that R1 becomes as equal to R2. In that case, P and Q will coincide with each other, and in that case, we will get the tangent at that particular point. Okay, and if by chance R1 and R2 both are complex numbers, then we will say that the straight line is not intersecting the curve at all. in that case, what would be the position of that straight line? This may be the position of the straight line. You see, this kind of straight line is not intersecting the curve at all. If this curve intersects, then R1 and R2 must be real. But if this straight line does not intersect the curve, then R1 and R2 would be imaginary. So imaginary R1 R2 would imply that the straight line is not intersecting the curve, and if this R1 and R2 are real, then the straight line would intersect in real points. Got it? So in this way, we can conclude that this kind of equation represented by a second degree general equation of second degree involving x and y would maximum intersect a straight line at two different points, at most two different points maximum. Okay, so this is the proof that a straight line may intersect this kind of curve at maximum 2 points. Now from this idea, I am trying to deduce the equation of tangent. Okay, but and if we get the equation of the tangent, we will be able to get the equation of normal as well. Okay, now how to deduce the equation of tangent? You see, as I told you earlier, that if the point Q moves towards the point P along this curve, along the curve represented by this red line, in that case we will have a tangent at the point P. Okay, and for such cases R1 must be is equal to R2. That's fine. If R1 becomes is equal to R2, we will get the tangent. But what is the relation in between R1 and R2? We know that R1 and R2 are the roots of this equation. So we can say that R1 plus R2 would be is equal to the coefficient of R divided by coefficient of R square with a negative sign. R1 plus R2 is equal to the coefficient of R, this much. This is the coefficient of R divided by coefficient of R square with a negative sign. So what would be the expression of R1 and R2? It is not written over here. I have written it in a separate file. This is the coefficient of R divided by coefficient of R square with this negative sign. Got it? So R1 plus R2 will have this kind of expression. Similarly, the product R1 into R2, the product R1 into R2 will be is equal to this constant term. Okay, this constant term divided by the coefficient of R square. All right. So this is the expression, this constant term divided by the coefficient of R square. Now in this kind of deduction, we will always follow certain notations. What kind of notation? Over here, we shall always represent this expression by capital S. Then capital S would be a function of these two variables x and y. Okay. Now in place of x and y, if we put x1 and y1, the expression we shall get will be designated by S1, and we shall follow one more idea, that is one more notation, that is the notation of t. What is this? How to construct the notation of t? You see, this this x square will be replaced by x into x1. Y square will be replaced by y into y1. Okay. Next, 2 times of xy. 2 times of xy will be replaced by x1y plus xy1. Then 2 times of x, twice x will be replaced by x plus x1. Next, twice y will be replaced by y plus y1. So if we apply this kind of replacement in the expression of capital S, we will get the expression of t. Got it? And therefore, this expression of R1 multiplied by R2 can be represented by S1 divided by the denominator quantity AL square plus twice HLN plus PM square. Got it? So R1, R2 will have a simplified notation. Now, if we get any tangent, in that case, of course, R1 must be is equal to R2. Okay. So in that case, if R1 becomes is equal to R2, this is the equation that we deduced over here. This is the equation number 3. Got it? I'm writing the same equation over here. This is the equation number 5 over here. So if by chance R1 and R2 becomes equal, then what we shall have? The discriminant of this equation must be is equal to 0. B square minus 4AC must be is equal to 0. So we apply the formula B square minus 4AC is equal to 0 means B square must be is equal to 4AC. That is actually the vanishing of determinant. If determinant becomes is equal to 0, then B square must be is equal to 4AC. So what is B over here? This much distance, this much coefficient, this much would be equal to B. So this is our B over here. Okay, and this is our A. So we write it small a, and this is our the total expression, suppose small c. So this is the idea that B square is equal to 4ac. So this left hand side is actually our B square. This is B square is equal to 4a and multiplied by c. So B square is equal to 4ac. Remember, in this B we have a quantity, the coefficient 2. So over here 4 would ultimately come on the left hand side. Okay. So B square is equal to 4ac will give us this kind of equation, equation number 6. Now in this equation number 6, we are going to eliminate small l and small m. Okay, we are going to eliminate small l and small m. Then what we get? What is small l? Over here, small l, you see, small l, this small l from equation number 4, this small l can be written as x minus x1 divided by r. Okay. Similarly, this small m can be written as y minus y1 divided by this quantity r. Alright. So if we now put these expressions of L and M in this equation number 6, then what we shall have? We shall have x minus x1 divided by r over here and y minus y1 divided by r over here. Similarly, on this portion we shall have this divided by r, this divided by r. So this quantity divided by r. Sorry, 1 r square would come over it. R square. This divided by r square. Okay. So over here we have both whole square. So on the left hand side, you see, on the left hand side, we must have 1 by r square. Similarly, if we consider r square common, then on this portion again we will have this kind of 1 by r square. So these two 1 by r square will get cancelled, and ultimately we have this kind of expression without any small r at all. So as because the small r would ultimately get cancelled, I am not considering any small r over here. Now we have certain computational trick or certain computational steps, important computational steps. What we are doing over here, you see, when this expression is multiplied by x only, we get this much expression. Okay. And when this expression is multiplied by x1, we are keeping them in a different group. This is the expression. Similarly, when this expression is multiplied by only y, then we are keeping them in this first group over here. Similarly, when it is multiplied by y1, we are keeping them in this second group. So this is the manipulation on left hand side. Okay, and we have this kind same kind of manipulation. This, what is this? This is our S1. This is the expression of S1. So I'm writing it as S1. Hmm. Now the expression inside this bracket, I am writing the expression elaborately, just making a group that a x square. This is the group of a x square. Similarly, b y square. This is b y square, and xy related term x multiplied by y multiplied by twice h. This would give us twice h xy. Okay. Similarly, we are keeping all the terms containing x1 square, x1 y1 and y1 square in a separate group, and the remaining terms are kept over here. Remaining terms are kept over here. Hmm. So now what we are doing, you see, on the left hand side, on the left hand side, if you observe it little bit carefully, we have h x1 y1 h x1 y1, so they would together construct twice h x1 y1. Hmm. And ax1 square is there, so ax1 square, then by1 square is there, we have by1 square, and the remaining terms gx1 and fy1 is there. But we expect that certain quantity like twice gx1 should appear, twice fy1 should appear, and plus c should appear, so that we will have the expression of S1 that should be adjusted accordingly. Okay, that should be adjusted accordingly in the next step. Now look at it very carefully. In the next step, what we are doing, we have these 2 and this C. That means we are adjusting something. So minus, we previously we had only a single gx1, but now we have twice gx1. So one extra g multiplied by x1 has to be adjusted over here. Got it? Similarly, over here we have 2fy1 with this negative sign. You see, with this negative sign, we have 2fy1, but previously we had only one single fy1. So we need to adjust one more f multiplied by y1 over here. So these are adjustments. Again, we have extra one more c with this negative sign. So we need to adjust this negative c and write a positive c over here. So in this way, we are making all the adjustment on the left hand side. Okay. Now on the right hand side, what we had, we actually had this much ax square plus twice hxy plus by square. Hmm. We are now making certain adjustment, twice gx plus twice fy plus c. These are extra terms. Again, over here, so this expression has to be adjusted, twice gx twice fy plus c. How did I adjust it? Over here you see we already have a minus 2 sign. So with this minus 2, we are multiplying g into x and f into y, but we have only a single c. Over here we have only a single c. Okay, And in order to adjust this single c, we are making few more adjustments. Over here you see a x1 square plus twice h x1 y1 plus b y1 square is there. Okay, but we are in this last line we are writing twice gx1 then twice fy1, huh? And then one more extra c. So this c and this extra c, they would be adjusted with this minus 2 into this c. So hopefully this is clear to you that plus c plus twice c minus twice c is now c is now totally adjusted. And then twice gx, it is adjusted with this g, twice gx1 is adjusted with this g multiplied by x1 with this minus 2, and twice fy is adjusted f multiplied by this y1 with this minus, sorry, with this minus 2. Got it? So in this way we are now able to adjust the expressions, and the last term was s1, so I am keeping this expression as s1. Now what we have, if you look at the expressions very carefully, this expression is the expression of this expression, no, not this expression. On the left hand side we have this kind of expression, but this is not exactly same as the expression of t, capital T. Is it so? Let's check. We had ax1, okay, fine. Then hxy1 plus hx1y. So we got this much term. Fine. Then byy1 is there. Okay, fine. We got byy1. But what we have? We have a single gx and single fy. But we should have gx1. So we need certain adjustment. What is the adjustment? This term with this negative sign, twice gx1 has to be adjusted, and that is kept over here. We actually had a single gx1. We actually had single gx1, but over here we have twice gx1. So one gx1 is adjusted with this term gx1. Similarly, over here we had fy1. Hmm. But we have twice fy1 over here, twice fy1. So that is adjusted with this f and with this y1. Okay. And you see, we do not have any small c at all. So over here we are writing a small c added and then subtracted with this negative sign, subtracted small c. So in this fashion, we adjust the entire expression, and now we are ready to write this entire expression as the expression capital T. And this is the expression of capital S1. Got it? So the left hand side can be written as T minus S1 whole square. And similarly, on the right hand side, this is the expression of capital S. Then this is the expression of capital S1, and this is the expression of capital T. So we can say that the expression within bracket can be written as S minus twice T plus S1 multiplied by this S1, of course. Okay. Now we expand it, and after cancellation of different terms, we got this term T squared is equal to SS1. T squared is equal to SS1. So we expect that we get the equation of tangent. If we now expand it, this is the expression of t, this is expression of s, and that is actually s1. You see, but look at this expression very carefully. This is not the equation of a straight line. Again, I am saying that this is not the equation of a straight line. What we get? We expect that we should get certain tangent line. So we should get certain equation of straight line, but whatever we got is not an equation of a straight line. Why? Because certain second degree x square, xy and y square related term would be present, which would not cancel out at all. Left hand side expression and right hand side expression would not cancel them out. Then what we get over here? What we get over here? That is a question. We actually get a pair of straight line, and we were expecting a single tangent. That means we were expecting a single straight line, but we get a pair of straight lines. So what we actually get, let me write one more picture for you. Suppose we have a certain conic, okay, and now suppose we are drawing two straight lines. This is one straight line from a point, and suppose this is another straight line from the same point. Got it? So we actually get two different tangent lines. We actually get two different tangent lines, and you see from a single point two different tangents can be drawn. So we actually get two different tangents through this equation. So we can say that this is actually the equation of the pair of tangents drawn from this line. This is one tangent and this is another tangent. We actually get the equation of a pair of tangent, and that equation would be this kind of equation: t square is equal to s1. So this is actually a standard formula. You please remember this formula: t square is equal to s1. Got it? So in this way, we actually get a pair of tangent. This is the pair of tangent. Now the question is that how do we obtain the equation of tangent? I am coming to this point one after another. Okay, you have to have certain patience, because I can't skip all these deductions. Hmm. I have, for the timing at least, I am skipping the idea of director circle. Although the idea of director circle is closely related with the pair of tangent, but for the timing, I am skipping the idea of director circle, and I am trying to directly go to the deduction of tangent. Got it? Then how can we deduce the equation of tangent? Hmm. Let me write any one more picture for you. Can we write this picture? Let's check. Let me write one more picture for you. Suppose this is the car, and firstly, in order to draw a tangent, we need to have these two kind of points. One point would be this kind of point P, another would be this kind of point Q. Okay, so we should have these two kind of points. Hmm. Now suppose this kind of point, this point previously the point capital A was taken in this kind of position, but now I am taking this position of the point capital A in a different position. Suppose capital A is this one. This is somewhere over here, maybe this kind of position, maybe the position of tangent. This is position of the point capital A, maybe somewhere over here. This may be the position of the point capital A, the fixed point capital A. Suppose this is the position of this fixed point capital A. Okay, in that case this would be the distance r1, and this would be the distance r2. This is r1, r1, and this might be the distance r2. Then you see, if one direction is taken as the positive direction, suppose this direction is taken as the positive direction, then opposite direction would be negative direction. So R1 and R2 will have two opposite direction. Just compare this straight line with x-axis. Suppose capital A is the origin. If Q along the positive x-axis, the position of Q is measured, then R1 would be positive and R2 would be negative. And in that case, what we expect that over here, you see, what would be R1 plus R2? If this is both, if capital A is in this way, in this position, and you see R1 plus R2, we are actually trying to find out the value of R1 plus R2 as the point Q, as this point Q is coming to the point P along the curve. Again, I am saying in the limiting position, as the point Q is moving towards the point P and ultimately coincides with this point P, then we are interested to find out the value of R1 and R2. In fact, if this point Q moves towards the point capital P, in that case, R1 must be is equal, R1 plus R2 both must have same kind of value, and that all these values must be equal to 0, because in that case, if the point Q coincides with the point P and their middle point A would also coincide with the same point P, I am saying again that if the point Q coincides with the point P, if the point Q moves towards the point P along this curve, then we can say that this point P, in this point Q, would coincide with this point P, and of course, some any intermediate point like A would also coincide with this point P. In that case, R1 must be is equal to 0 in that limiting position, and R2 must be is equal to 0, so that R1 plus R2 would also be equal to 0 when the point Q moves towards the point P and ultimately coincides with the point P. Is it clear to you, everybody? The remaining portion is just matter of calculation. Is it clear?
স্যার R1 plus R2 0 ওই জায়গাটা আরেকবার বলুন না।
আমি বলতে যাচ্ছি that as the point Q, when the point Q is different from P, R1 is not equal to 0 and R2 is not equal to 0. But when the point Q goes towards the point P in the limit along this curve, when the point Q moves along this curve, okay, and ultimately for tangent, what we should have? Q must be coincident with this P, that I already demonstrated in this first picture. You see, I told you earlier that this kind of straight line, this is the point P. So as the point Q moves towards the point P and ultimately coincides with this P, then this curve will become coincident with this tangent. This straight line will become coincident with this tangent. Therefore, in order to get this tangent, we must take the limit Q towards the point P, Q tending to P along the curve. Is it now clear? What I am trying to
Yes, sir.
say, Q should tend to the point P, and in such limiting position, in such limiting position, R1 must be equal to 0 and R2 must be is equal to 0, because all the intermediate points like capital A would also coincide with this point P. Correct? And in such cases, R1 and R2 must be same, because as this point Q moves towards the point P, this line, you see, this line is changing. Now you see, the length of this line is decreasing, and ultimately it becomes is equal to 0. The length of this line segment, in distance in between P and Q, would ultimately become is equal to 0, and therefore any intermediate point that would be situated over here in this kind of position, okay, that this distance, that kind of distance would also be equal to 0. Got it? So R1 must be is equal to 0 and R2 must be is equal to 0 as the point Q moves towards the point P. And therefore I am saying that in this limiting position, R1 is equal to 0 and R2 is equal to 0. Therefore, R1 plus R2 is equal to 0. Now, is it clear to you?
Yes, sir,
Any
clear.
Do you have any other further question over here?
No.
Okay, so now remaining portion is actually the matter of computation only. Hmm. So over here, R1 plus R2 is equal to 0. Okay, R1 plus R2 is equal to 0. R1 plus R2 is equal to 0. That means the numerator in the expression of R1 plus R2, what was the numerator? We had this kind of expression. This is the numerator of R1 plus R2. So this numerator must be is equal to 0. Hmm. So we have the result that this numerator, sorry, this expression, this numerator is equal to 0. So 2 get cancelled. And now we are trying to eliminate small l and small m, just similar to the technique as we eliminated small l and m. So x minus x1 by r and y minus y1 by r should ultimately come over here. Hmm. So we actually have x minus x1 divided by r, y minus y1 divided by r, and that r would ultimately be cancelled with this right hand side. So I am not writing this r over here. And now remaining portion is actually the matter of adjustment. That's all. We are expanding this expression. This is the expansion of multiplication of this expression with x and multiplication of this expression with y. Okay. Similarly, when we multiply this expression with x1, we get this expression, this much expression. And similarly, over here, when we multiply this expression by y1, we get this kind of expression. Hmm. And then we have a similar adjustment over here. Ax1 square is there, ax1 square. Then by1 square is there, by1 square. Then hx1y1 and hx1y1 put together construct twice hx1y1. Hmm. And remaining gx1 is there. So single gx1 is there. I am writing twice gx1. Got it? And this twice gx1 is adjusted with this g into x1. Similarly, over here we have fy1, a single fy1, but we are writing twice fy1. So that is actually adjusted f into y1. And then plus c and then minus c because we have a minus sign over here. So in this way, we are adjusting the result, and so we ultimately have the result that t minus s1 is equal to 0. So we have t is equal to s1. Now, what is s1? You see, remember this is very crucial part. What is x1 y1? X1 y1 is actually the coefficient of this point capital A. And I told you that as the point Q converges to the point P at this point, then this intermediate point A should also again come to and coincide with this point P. So we can say the coefficient of A and coefficient and not coefficient, sorry, please excuse me, the coordinates of A must be equal to the coordinates of P. Okay, as the point A becomes coincident with this point P, therefore the coordinates of the point A must be equal to the coordinates of the point P. All right. And therefore we can say that capital A or capital P must satisfy the equation of this curve, because the point P lies on this curve. Therefore the coordinate of the point P or the point capital A all are same. The coordinate of the point P or the coordinate of the point capital A must satisfy the equation of the curve. And what is the equation of the curve? Equation is S equal to 0. Hmm. And if x1 y1 lies on this curve, capital S on in the limiting sense, of course. Hmm. In that case, we must have S1 is equal to 0. Got it? We must have S1 is equal to 0, and that's why we put S1 is equal to 0. And so we actually have this equation T is equal to 0. This is the equation of tangent. T is equal to 0. So please remember that T is equal to 0 will give us the equation of tangent. Got it? You need to remember this formula. T is equal to 0. That would be the equation of tangent to the curve S is equal to 0 at the point x1, y1. Now we want to find out the equation of tangent. What is tangent? Tangent would be a straight line that is what is sorry, the normal is sorry. We want to find out the equation of normal. We got the equation of tangent. We want to find out the equation of normal. This is the position of tangent. Got it? Then what would be the equation of normal? This kind of straight line. This kind of straight line, not perpendicular. I'm not writing. I'm not good in this. So this kind of straight line would be the equation of tangent. This kind of straight line would be the normal. Tangent is the green line, and normal is the this kind of red line. Got it? So this is normal and this is tangent. Hmm. Now we want to find out the equation of normal. How to find out the equation of normal? Firstly, we need to compute the equation of the gradient of tangent. This is the gradient of tangent. M is equal to this. You see, this is the coefficient of x and this is the coefficient of y. Therefore, we get the equation. We get the gradient over here. So in this way, we will get the expression of the gradient of the tangent. Then what would be the gradient of the normal? The gradient of the normal would be is equal to minus 1 by m. That would be the gradient of normal. So what would be the equation of the normal? X minus x1, this expression, and over here y minus y1, that must be is equal to minus 1 by m into x minus x1. So in this way, we will be able to compute the equation of normal. Is it clear to you? The equation of normal? Could you follow?
Yes, sir, clear.
So to finish with this result, just I want to say that if you look at this expression, of capital S, hmm, and if you differentiate this expression with respect to x only, forget about y, consider y as a constant quantity, then the kind of derivative is actually called a partial derivative, and that is actually the notation del x. This is the notation of partial derivative. Probably you didn't have the idea of partial derivative. Anyway, so sometimes what we do, we actually keep one variable as a variable quantity. So x is a variable quantity, and the remaining all the other variables present in that expression over here. Remaining variable means y. If so, if we consider this y as a constant quantity, and then ultimately it would be a function of x, a single variable. And if we differentiate this expression, if you see over here ax square is differentiated, you will get twice ax. Then twice hxy. X is the variable, not y. Y is a constant quantity, so you will get twice hy. Then by square. This would get cancelled under derivative. So twice gx would give us twice g. Twice fy would get cancelled under derivative or partial derivative with respect to x. And then c would get cancelled. So we shall have only three terms. Got it? So three terms in partial derivative. So this is the expression of partial derivative. Similarly, we can have the partial derivative of y. This would be the expression of partial derivative. And forget about this 2. You see, you will get the coefficient of x and coefficient of y at that particular point. If you put x is equal to x1 and y is equal to y1 in these two expressions, you will get the coefficients of x and y. Hmm. And These are the coefficients of x and y. These are the coefficients of x and y. Hmm. And now, if you consider this expression of normal at that point, then you will see under computation, this expression can be written in this way: y minus y1 by hx1 plus by1 plus f, that is equal to x minus x1 plus that divided by ax1 plus hy1 plus g. Hmm. And multiply these denominators by 2, then you will find that this denominator would be the denominator that is actually the partial derivative of y at the point x1 y1. Similarly, x minus x1 is divided, and that denominator would be the partial derivative of s with respect to x at the point x1 y1. So I would advise you to remember this kind of expression, because this kind of expression will be very useful if we extend the idea of tangent and normal to three-dimensional geometry. In three-dimensional geometry, we actually have the same kind of notation. So I am trying to make you acquainted with the idea that you will encounter in three-dimensional geometry. Got it? So it is my advice that whatever complicated expression you have, you please remember the equation of normal as this kind of expression: y minus y1. It is divided by partial derivative of s with respect to y. Okay. Similarly, x minus x1, it is divided by partial derivative with respect to x. So that's all in for this lecture that I wanted to discuss with you. Now, let me finish this lecture. Thank you for having patience.